last time.
Okay, so I basically took the table and I put it into these bunch of numbers, right? Now, this is a satisfying assignment for that formula. What we'll do is we're gonna circle all of the variables that we picked, right? Now you guys get why these are ones, right? The reason why is because there's no way we can assign, if I picked x1 and x1 bar, right? So you see for a given column that only refers to one, the first four columns refers to each variable, right? I can't pick its variable and its complement. That's impossible.
Yeah.
Basically, I would be saying x1 is equal to 1 and x1 is equal to 0, which is impossible. That's why we're constraining the first four to be ones.
Yeah.
You get that?
Yeah.
Okay. Now let's look through the first column, right? We get 1. So this column refers to clause 1, 2, 3, and 4, right? 1, 2, 3, and 4.
Yeah.
Okay. So clause 1, we got 1 here, so that's 1, and that's it. Oh, fuck. So we only have 1, 1, right? Okay, we have 1, 1. Well, we need the sum to be 3. What can we do?
At the bottom.
There are 2 more ones here, over here. We're going to take those 2,
Yeah.
right?
Question. Why? So what if we just made the targets all ones and then removed C1 to C4 bar?
Right.
Okay, but if you look at it from like a different perspective, right? You make C1 and C1 bar equal to 1, 1,
Yeah.
and you set the bottom to 3, right? What that's gonna impose is, right? It means that we know for the last 4 columns,
Yeah.
each column corresponds to 1 clause,
Yeah.
right? And that means because we set the bottom 2 to 1,
Yeah.
and we want 3 at the end, that means that we're only allowed to add 1 more to that column.
No, what I meant was
Okay,
if that column here.
So you're saying make those 1.
And then remove C1 to C4.
Right, okay. Now let's look at this case.
Yeah.
You have 1 plus 1. This is a satisfying assignment, right?
All right.
What's 1 plus 1?
2.
2. But, I mean, this
But
works.
but that's
This works, but now 2 is not equal to 1. What do I
okay.
do?
But it's 3
But
there.
the reason
so
why we have these guys is we have, for each one, we have only exactly 2.
because
So
it's
if there's 1,
Yeah.
we can take 2 of these guys. If
Okay.
there's 2, we can take 1 of these guys.
And
If there's 3 in a column, we don't need to take any.
Okay,
But
so
if
these are just the fillers,
Yeah,
right?
They're fillers, that's why they're called dummies. But if there's 0 on each case, even if you take 2 of them, you're not going to make it to 3.
Okay.
Right? You guys get that?
Yeah.
Again, sorry?
So you
So
gotta
if-
change C3 or C3
So if,
bar to
for a
0.
given column, if we have 1, 1, means that we have 1 variable that's true in that clause. So we'll pick 2 dummy variables. If we have 2 1s in a given column, then that means we can take the 1 dummy variable here on that given column. If there are 3 1s in the column, we're good at 3. We're set at 3. Now, let's say we have 0 1s in that given column. We could take 2 of the dummy variables, but we'll never get to 3 because there's only 2 dummy variables.
But I thought we always set the dummy variables as 1, 1, 1, 1, 1, 1, 1.
Yeah, 1 1.
But
1, 1,
that
1,
third
1,
row,
1, 1.
the third from right column, we have 2 1s at the top and we have 2 1s at the bottom.
This one?
X2 bar and X3 bar,
So x2 bar.
and X3 bar second column from the right.
Yeah, we have 2 1s.
2 1s and then at
Okay, so
C3.
let's go back. So we had 1 1 here, and that's it, right? So
Yeah.
we have to take these 2, right?
Yeah.
That's part of. All right. Next, for this column, how many 1s we have? We have a 1 here, right?
Yeah.
Which means that which
You gotta
one do we
take 2.
We have to take 2
Yeah.
as well, right?
Yeah.
One now. Let's say that we have the third column. We have 2.
Yep.
Which one do we take? Any one of these.
Oh, you only pick one.
One.
All
You
right.
only pick one, right?
All
you have
right.
to get the sum to 3.
Okay.
Last one is you have 1, 2. You have 2 1s, so you just pick the last one.
Oh, okay.
Now, this is why it relates to subset sum. These were 1s and 0s in the table.
You get that?
But what if this
So you
was?
just pick one for
What
each
if
one.
I told you that this is a numbered decimal?
Okay.
Right now, the numbers I square. Now,
Yeah, you can set dummy variable to 0.
if these are numbers in decimal, not binary, decimal,
So
okay?
the first column.
Then what am I trying to do here? I'm trying to find a subset of these numbers such that I get this number.
Yeah.
That's it. That's subset sum.
Yeah. But we didn't show that any solution for a general case of 3 SAT will
Right.
can be
So
solved in this subset.
this is what you do, right? basically in general. But you get why this is. You guys all get why this is subset sum, right? If these numbers represent decimal numbers, our target is always going to be 111,333. We're trying to find a subset of these numbers that add up to 111,333.
Yeah.
Right? That's why it's subset sum. So we've reduced 3 sat to subset sum, where the function is this, right? The function is
at least one for each
that
cohort,
if I have m literals and what did I say? And clauses.
So we have to like pick at least one.
Our mapping is that we need
two, but at least one of these three.
we need
Yeah, because some will
2m
exist too. Exactly. So
plus
that's why.
2n
So it's always
variables,
satisfied.
right?
Yeah,
2m plus 2n
But
variables,
we can always
and
select the
then
three.
we have to set up the variables such that they look like this, right? Such that the same way we set up the variables the same way we set up the table, and then that's it, right? That's our function.
Makes sense.
But
Okay.
Alright.
Did you guys all get subset sum now?
Yep.
You get it? You sure?
So how do you
Wait,
do
so
it?
does that last part prove like the general case?
Yeah. So in general, basically, so this was a special case,
Wait,
but
what was
in
the
general,
last thing you
in general, what we need to do is this.
what's the 2m plus?
Yeah. Okay. So let's say we have any function f, right? Any Boolean 3-sat Boolean function f. Okay. What we'll do, our function, our algorithm f, which I'm referring to as this algorithm, is this. We'll need to set up 2m plus 2n numbers in our set, right? So remember, subset sum is we need a set, right? So our set will have 2m plus 2n variables, right? So it'll be x1, x2, all the way up to x2m plus 2n, right? So that's going to be our s, right? Where x1, the first x1, the first 2m variables, so x1 through x2m, are set up like this, where you go through the table and you set up the decimal number the way we did, and then x of 2m plus 1 to 2n are just the dummy numbers, and then we just find given this set, find the subset. That's it. Right? Now you guys get it?
What is the x1 dot x2m x?
So these are the first 2m variables, which refers to this guy. So our mapping will find x1 through x of 2m such that it looks like the way it does in the table, right? You take the table, you make the literals, clauses, make the ones and zeros.
The
Yeah.
first n is gonna be mapped at 1 1 1, the second n.
Yeah. And then those last ones are the dummy variables. So that's our mapping. Yeah.
Wait, so then to do it the other way around, do we just like take those decimal,
Yeah.
like for those decimal numbers and then convert them to binary and then?
No. So our forward implication is that given subset sum, given there's a satisfying assignment, we've guaranteed that we will be able to find, we'll guarantee that we'll be able to find a subset that adds up to 111,333. By the way, the target is equal to 1, 1, 1, 3, 3, 3. That's our target. So our mapping function makes that, that's always our target, where there are 2m 1s and 2n 3s.
n 1s and n 3s?
Sorry, yeah, you're right. M1s and M3s, yes, correct. M1s and M3s. And how many? There are
Yeah, you're right.
yeah, M1s and M3s, right? So given that we have a satisfying assignment, we're guaranteed to find a subset sum. And given that there is some sort of subset sum, we know that whatever subset sum we pick, if the variables are from x1 to x2m, that's going to be our satisfying assignment. Do you get that?
Yes.
So
You
if we
did that
found,
last sentence.
okay, so if we found a subset sum, right? So let's say it's a generic problem, and our subsets, let's say we have this guy, right? And then we had our target value as 1, 1, 1, 3, 3, 3, right? Now our subset sum was x1, x3, x, 2m, and then x 2m plus 2, x 2m, I don't know, something like that, right? So these guys over here are the dummy variables, so we don't care about them. These guys will be the values that are going to be true in the satisfying assignment, and then the other ones that weren't picked by the subset sum will be zeros. will be zeros in the satisfying
That's the
assignment.
backwards implication, right?
Yeah, exactly.
The forward implication would
Yeah.
be, given your,
Your satisfying assignment,
you
it will end up being a
create
subset
this,
sum.
and then you create this, and you pick each
Yeah.
row that corresponds to,
Yeah.
like
Exactly.
x1 is 1, then you pick x1.
Yes,
x2
yes.
false is 1, then you
Right.
pick x2, and you add those and you get.
Yeah, exactly. So let's review that one more time. So,
convert
so
it, bro.
the forward implication is this: you have your satisfying assignment. Whichever ones are true, you pick this one's here, and then you pick its corresponding dummy variables, and that is guaranteed to form a subset sum. The opposite direction. Let's say we didn't square these ones, right? And let's say we didn't care about the satisfying assignment. We just blindly picked rows such that it added up to 1, 1, 3, 3, 2,
Yeah.
without regard to the actual satisfying assignment.
Yeah.
So we just looked at this and we happened to find a subset sum.
Yeah.
If we found whatever subset sum that we ended up squaring will be the corresponding variables in the satisfying
Yeah.
assignment.
So for in the other implication,
square?
is it sufficient to show that okay we pick x1, x,
So,
x
yeah.
or x2? Oh
Yeah,
no,
so
no.
we
Oh, yeah.
look, our
We need- yeah.
formula was this guy, right?
Yeah.
So don't look at this formula and just look at this table
Yeah.
and find the subset sum.
Yeah.
Don't disregard that formula.
Yeah.
Just find anything that works here.
And then you will.
And then if I found anything that works,
Yeah.
whatever, I look up here, I ignore the ones that I picked below here, because those are dummy variables, we don't care
Yeah.
about them. Anything that I picked above here, let's say I happen
Yeah.
to pick this guy, this guy, this guy, and this guy,
That
so
will-
these are gonna be,
that will be true.
ones in the satisfying assignment, and these guys are gonna be zeros in the satisfying assignment.
Yeah.
That's the backwards implication. You guys get that now?
Yeah.
One more?
That shows it works, but it doesn't. It's not a.
Homer, you
proof.
got it?
No,
Right?
100%, no.
It is a
What's
proof if
your
you
question?
write it like formally, yeah.
Is it a proof? Oh, if
Yeah,
you,
it's it.
Whenever
if you
choosing-
write, oh, if you select
What's your question?
any sum, then
Whenever
it will
choosing
work.
this one
Yeah, yeah.
and getting that
Okay,
one,
yeah.
how,
I
how
think the
does-
most important part of your proof
Because I
is
guess what
explaining
we're doing
the
there, I
function
guess
f.
like,
And
the
then
first, even
it'll
for
be
the
like
first
you write
column,
whatever the
we're
fuck you
choosing
want after that.
x1,
Wait,
and
what
that's
if
all,
the
because that has to be
numbers aren't
one.
like ones and
For the
zeros,
second
though?
column, you're choosing
What do you mean,
x2,
here?
for third column is x3,
Yeah.
fourth
No,
column x4.
for these guys?
And there's the one, there's the limitations there, right? What are we doing
No, what
with
are you
those?
talking about?
Choosing
So-
those,
so
what
when
are we
I
doing
pick-
with that?
When I find myself, we're talking about the backwards implication.
Yeah.
Are you talking about
When I
forward
find
or
the subset
backwards?
sum, what was your
Forward.
question?
Forward.
Yeah.
So like look
Okay,
for the
so
subset
forward,
sum,
forward,
Yeah.
right?
there's so many different
You-
numbers, right?
Yeah.
You are given
So would
your
x1
F
represent a
preset,
number?
and
Yeah,
you
x1
know
is a
you can
decimal
give it
number.
you can be
Okay.
given
Decimal,
a
not binary,
assignment
decimal.
for x1
Yeah,
through
so like
x4,
if it's a
right?
decimal number, like
And then
what if they're not just ones and
The
zeros?
corresponding
It's like
row for
two-
x1 through
Okay,
x4.
so, remember when I said, I think
If
I said
x1 is equal to
that
1,
what you're
then you
doing
pick
here.
x1. If x2 is
So
equal
that's your
to
confusion,
0,
okay?
then you pick x2 not,
Yeah.
right? And so you select, let's say we chose x1, x2 not, x3 not, x4, right? So that's what we got from the 3 set, right? And now, if you, by selecting those, right, what we can do is we can add those numbers together, and then we can pick appropriately whatever we need from the dummy variables. So let's say we pick by picking those, in the first column, you see your sum is only 1, right? So you need to add 2 more to get your sum to 3.
Yeah.
So you pick 2 dummy variables with ones in those columns.
Okay.
Yeah.
But
So,
if
Denzel.
the sum in that column.
Okay, so
is, let's say,
Denzel had a good
2,
question, guys,
Okay.
which is one of the confusions I was going at, right? So, he's saying that if, let's say we're going through the backwards implication, right? And we're trying to find a subset sum, right? He's saying that what if the numbers of our
Backwards
subset sum
implication
is finding subset sum? If we find subset sum of this guy, then we're
it's
guaranteed
given a
to.
subset sum, find the
Exactly.
implications of.
Yeah. So he's saying, what if the numbers were not 1, 0, 0? What if they were like 2, 2, 2? Because remember, subset sum is just any sub, given any set, right? What if the set was like 2, 3, 4, 5, right? Or something like that, right? Which can't be written as that, right? But that's the thing, though. That's the thing. That's confusion, right? We're trying to reduce this to that, right? So we're looking at
Any problem
Yeah.
in 3-SAT?
Okay.
any problem in 3-SAT reduces to subset sum, right? So
Okay.
here, in this
Split it
case,
apart.
our function f is taking every problem and mapping it to only a small set of problems.
Actually, just
in
one
B.
problem, right?
One small, only small.
Small set.
This is a very small set. We're only concerned with subset
Because
sums
it's-
such that the numbers are zeros
Oh, yeah,
and
yeah.
ones,
Yes, that's
right? We're only concerned with subset sums such that the numbers are 0 and 1s. So that's our small set in B. We're mapping everything in A to a small set in B, right? if we wanted to do it the other way, then we're taking any general number and mapping it to a specific three-sat formula.
When you,
Wait,
when you're doing
backward
the forward implication, you do given an x, right?
Yeah,
You have f of x such that it satisfies b, right?
Yeah.
And so given anything in A, you have that small subset which also satisfies b. But when you do the backwards implication, you only need to do for any f of x element
Yeah.
of b,
So-
you have an x.
so this- yeah.
only something in that small subset.
Yeah,
for
yeah,
A,
only
yeah.
something in
Only
this small
something
subset.
that looks
Also
like
one and
this.
zeros.
Yeah,
Anything that
also-
looks like ones and zeros. So we're mapping general problems in A to a small set in B.
And
That's
would,
why.
would like subset sum be considered like a harder problem than?
Yeah.
Yes.
So whatever you're reducing to is the harder problem.
Yes.
And the reason why it's harder in this case is because of like, there could be like twos
So
and
you're
threes
not
and
smart.
stuff, or that.
Yeah. So yeah.
No, yeah, this
Because
is
because
right.
A is a restricted problem of B, right? So if I give you problem B and I give Dexter problem A, you can convert your problem into Dexter's problems by restricting it to such a
So
problem.
like, the
Right?
small set of like.
Yeah.
inputs.
So you got, yes, that was a good question. Now we cleared that up. So this, just by proving this way, we're not
Okay.
reducing, they don't reduce each other.
So for Omer, you pick, so given as satisfying for f, right? You pick x1, x2 bar, x3 bar, x4 bar, right? And then let's say you look at column 3, you have a sum of 2 already, so you only pick one of the dummy variables, right? And once you're done circling all of them, right? Then you have all these numbers. So x1 is a number, right? So you have, I think that's 10,000,001, right? And then x2 bar is another number, it's 1,000,010, right? And like that, you have all the numbers you circled. If you add them up, you're gonna get that number at the bottom, which is 1,111,33333. You get it?
Mhm.
And so you basically, so the set of all numbers in this case is all of these numbers is the set of all numbers, and you've basically found a subset of these numbers such that it adds to a target number, which
Yeah.
is the 1,111,33333.
And then that
I think I get
translates
it.
to.
You get it?
I think I get it.
And remember,
I haven't practiced, but
when we're
I
going
get
to
the
the
main
backwards
idea.
implication, we don't
We don't
care.
feel-
When we're finding the subset sum, we don't look at the three-sat formula. We're just looking at this table and finding a subset sum. Now,
So-
whatever
so-
subset sum we find will happen to be a
How
three-sat.
do we guarantee that? How do you know that?
Because by the
That's the proof
That's part of the
itself,
proof,
right?
that's a
So-
proof itself.
So given
Yeah.
some problem like this, right, you first say you only look at problems which is a subset of f of x, right? So not all of b, but f of x of b. So a problem like this, right? You will be given an f of x such that it satisfies b, right? So let's say given this, it gives you that you figure out that these numbers, you can add them together and get this, right?
We're given f of x.
Yeah, because it's like when you're proving implication, right? You're proving forward implication, you assume you have this, you prove this.
Okay.
When you're proving backwards implication, you assume you have this and you prove this, right?
Okay.
So in the backwards implication, we assume that we have an f
So we
of
basically
x
have the
which
exact same
satisfies-
subset.
Yeah,
Wait,
you're
what
gonna
if we're going backwards?
I don't know if it will be the exact same, because that goes
Oh,
into
yeah.
like uniqueness, right? Is the thing
Yeah.
unique or not? But you will have some solution.
Yeah, would it be unique?
What do you mean by unique? Like,
So like in forward, right? So we had a logical
three-sat.
expression
Yeah.
that's 3-sat, and then we convert that into that chart, right?
and then the chart.
A table.
No,
Yeah.
it's not necessarily unique because any logical expression it can have multiple satisfying variables, right?
Right. Sure.
For instance, if I give you like x1
Yeah,
or
yeah,
x2,
yeah, yeah. And then
right?
x1, x2, x3, x4 was these.
Yes,
particularly.
this was our satisfying assignment, and then these are the ones that are going to be selected in the subset
Yeah.
sum.
But let's say you so you can also be given your subsequent problem and you'll be given an f of x which satisfies, which might not be these, right?
Wait,
It
what's
might
our
be
f of
like
x here?
F of x is our tables of ones and zeros, so variables of ones and zeros. So you're given a set such that each number looks like this. That's our f of x. A set
The
S.
set is our f
A
of
set
x.
S such that all numbers look like this, where the first half of the numbers correspond to ones and zeros of the clauses and literals, the second half are dummy variables, and T is equal to 1, 1, 3, 3. That's our f of x.
1, 1, 1, 3, 3, 3.
Where there are m1s and n3s. That's our f of x. We don't care about other subset sums.
Our subset is what? The first half?
So subset sum So f of x is a
Yeah.
subset sum.
Right.
Not just any subset sum. Only a special case of subset sum where t is equal to, in this case,
Oh, I
1,
see.
1, 1,
Okay.
1, 3, 3, 3, 3. Only that type of subset sum.
Okay.
And where s, where the set of numbers looks like this. Something like this.
Yeah.
So you're saying x, I think we had
Oh, I
this question
see.
before. You're saying, like last session, you're saying x elements of A means that x is a problem of style A.
No, x means that, x of a means that x is a yes, x is
X
an
is a
input,
yes
and
instance.
x is a yes instance.
So that would mean that f of x is a yes
Yes.
instance of B.
So
So
if
f
I-
of x would be the exact subset.
Yeah.
Right.
Sums up to instances.
And that is possibly polynomial time.
Okay, I don't even understand the problem.
Why are they going to the like?
Wait, what's polynomial
Done.
time?
F is computable in
Or how
polynomial
are
time.
the
So what are we computing?
problems
We're
like?
F
I
is
can't
a-
figure out
not
this shit by
computer.
myself.
F
They
is a
made
algorithm.
they made a
No,
table.
this was
That
discovered,
where
they
T
got
is one, one,
PhDs
one,
discovering
three,
this.
three.
So, yeah, so
Given a
F is
subset
a-